Okay, let's begin. Yeah, firstly, let me clarify something. I think this created some confusion in the last class. So this was the common source with the current source at the top. So again, as I mentioned, nominally you try to bias it so that the operating point current in the transistor is also I0. But I mean, as we'll see, it is not possible to independently set two current sources to carry same current. But let us say we somehow do this. Now on top of it, if you apply an increment delta V, if I draw the small signal equivalent, I'll have this delta I current, this dm delta V, and the output resistance R0, right? So what is the current flowing here in the output resistance? Yeah, minus delta I. So the output voltage is essentially what? Minus delta I R0, so that's basically GM R0 times delta V, right? I mean, right, but I think I kind of misunderstood some of the questions. See, the thing is, if you apply a increment delta V, you have an increment current GM delta V that is due to the gate to source. So that is going to flow to the output resistance. So if you try to find the total current here, what is it? What is the total current? In the operating point it's I0. Here it is delta I. Yeah, that is still I0. Okay. So the increment current due to VGS is still there, but the total current is still be equal to I0. Okay. I kind of misinterpreted some of the questions and might have told something.
How the total current is I0? I0 plus delta I, right?
No, totally, right? You also have the dependence due to R0, right? I mean, this is basically operating point which I am not ignoring, I mean, which I am not considering. In addition, if you have this, so total current is still I0.
So this whole block is I0.
Yeah.
Because the delta I current is going in itself.
Yeah. This delta I current is going to circulate within itself. So effectively, no incremental current flows here, right? But to the output resistance, you are going to have some incremental current flowing, right? And if you look at this picture, it should be clear. Operating point current is I0. Due to VGS, you have a delta I current. And to the output resistance, you have minus delta I. So overall, it is still I0. Okay. So hopefully this is okay. So then let's move on. So in the last class, we looked at poles and zeros in this 5 transistor OTA. So let me quickly do that. And in particular, we looked at poles and zeros in the differential mode, wherein I apply a truly differential excitation like this. We made a couple of assumptions. The first assumption was that we ignored the CGD for the transistors. And secondly, we assume that the output capacitance is much greater than the other capacitances and that the poles are all far apart. So that helped us approximate the pole location as, we can approximate the pole location as the conductance at a node by the capacitance at the node. And also when we are trying to find the zeros, we made another assumption. What was that? To make this voltage zero, we assume that the R0 of the NMOS, that is the R0 of the differential pair, we considered it to be infinity. This is basically for the diff pair. So this combined with the fact that we are applying a antisymmetric excitation resulted in the tail node to be equal to 0. So that simplified the circuit essentially. So this is ground, right? So you now only have 2 poles due to the 2 capacitors. Now although in principle you have a pole due to this guy, in differential mode under this condition that pole will get exactly cancelled by another 0, so that will not appear. So what are the 2 poles? What is contributing to the dominant or the low frequency pole? CL. And to find that pole, what do I do to the other capacitance? I'll open it. So this is what value? 0. Okay. So what is the dominant pole? It is the capacitance times the output resistance it sees. You guys know what that is. So I'll just write it as some G0 by CL. So the second or the high frequency pole is due to the capacitor C3 And to find this pole, what do we do to CL? We'll assume that it's short. So what is the pole? C3 is here, and what is the resistance looking here? It's 1 by Gm parallel R0 of this. The R0 has been ignored, so it's just 1 by Gm. So the conductance is Gm of the PMOS. You'll have only these two poles in the differential mode, and you also have a 0 that you can calculate it to be twice this non-dominant pole. Okay. So if you try to sketch the Bode plot, I'll roughly do that. So you'll have the first pole appearing somewhere here, and then let us say second pole comes here, and then immediately you'll have a 0 like this. So as I mentioned, overall you can still approximate it to be a first order system like this. Cool. So this is with the 5 transistor OTA. After looking at this, what is the next OTA we looked at? Yeah, we looked at the cascode to boost the output resistance. So let's look at the single-ended cascode first, and then we'll move to the telescopic cascode. So let me draw. So this is the cascode transistor. This is the main differential amplifier, transconductor. And let's assume that we have an ideal current source at the top for now. Let me label it M1, M2. So this is connected to some bias voltage. This is output, right? So firstly, what is the small signal DC gain? No, can you check carefully? What is the short circuit transconductance here? GM? M. You check, it's minus GM1. Okay. Times the output resistance you have, and what is the output resistance? Yeah, that's approximately, you guys know this by now. That's all. So this is something that you already know. So let's move on. Now let's try to add capacitors and see what will happen. So I'll say that this is incrementally short. I don't consider the bias, and the current source is also open. I will not consider it. And for considering the poles, even the input I'll short. So you'll find that you can basically lump all the capacitors into these two nodes. Any capacitor you have, any parasitic capacitor you have, can be lumped into these two, because essentially, this is short. Okay. Cool. Yeah. So now again we'll make similar assumptions. We'll assume that CL is much greater than C2 and the poles are far apart. So firstly, how many poles we will have here? 2 poles. We have 2 capacitors. We can independently initialize both capacitor voltages, so no contradiction. So 2 poles. So what will contribute to the low frequency pole? CL. So, and for this I'll consider C2 to be open, so I'll assume 0. So what is the pole? What is the pole location? The capacitance is CL. I open this guy. What is the resistance looking here? It is a cascode output resistance. So I'll just write it as some G0, where G0 is 1 by R out. Okay. That's straightforward. So now let's find the high frequency pole. And for this, what will I do to the dominant capacitor? I'll short this guy. So let me maybe short it here. I'll short it now. So the capacitance is C2. What is the resistance looking here? Yeah, looking down it is R0 of the transistor M1. Looking up it is 1 by Gm of M2. And looking up it's 1 by Gm2 because this guy is short. Okay. If let us say I don't have this case and I ask you to find the looking up resistance, what will that be?
Depends on what you can.
Yeah, right now there is nothing open, right? It will be infinite. Looking up its open circuit, whatever small signal voltage you apply, no current will flow here. remember, I mean, for if you have a case like this, what is the resistance, exact resistance? If I call this some RD,
R0 plus RD.
yeah, RD plus R0 by 1 plus GM R0. So if RD tends to infinity, entire thing will go to infinity. Okay, but in this experiment, I mean, in this case, since CL is short, drain is at a low impedance, we can approximate as 1 by GM. So the second pole, what is the location? Huh? C2 is a capacitance, looking in resistance is 1 by GM2, so this is basically GM2 by C2. Okay. Cool. So this is with the poles. Let's see if you have zeros. Let me erase all this. So let me draw the capacitors. For zeros, I need to mark the input and the output also. So V in, V out. Yeah. So let's see if we have zeros here. Do we have zeros in the circuit? Why? Okay, first of all, if I short CL, everyone is convinced nothing, output is 0. So what if I short C2? Why output is not 0? If I short C2, you have applied an incremental voltage here.
Incremental current will go into that short.
Yeah, so whatever incremental current is getting generated by the transistor M1, where will it flow to? It will flow to the short circuit. What will be the current flowing to the output side? 0. So output will become, so how many zeros we have? 0 zeros. Okay, so we'll have no zeros. Okay, so this is with the single-ended cascode. Let's make a telescopic differential cascode. Let me first draw this telescopic cascode. So this is the PMOS current source, PMOS cascode, NMOS cascode, and the transconductor. I'll have identical copy this side. So I'll make a direct connection like this so that we get a high swing cascode current mirror. Please recollect, we can also do direct connections like this, but that reduces the output swings. So we'll do this, and yeah, let me also lump all the capacitors. So the output, we have CL. So here we have other capacitors. I'll just mark them. So here again we'll try to find the differential mode transfer function. Okay, we'll make similar assumptions like we did for the other diff amp. First we'll ignore CGD so that there is no coupling between each network. That simplifies. Secondly, we'll assume CL is much greater than other capacitors. I'll call it all CIs. And as usual, poles are assumed to be far apart. And once again, we'll assume that the R0 of the NMOS is infinity. That is, this guy's R0 is infinity. So that will help us say that Vx is 0. So once again, we can say that this is ground. So we don't have to worry about the capacitance at this node. At least that will simplify things. So let's not calculate in detail all the poles and zeros, but let's get a qualitative understanding. How many poles we'll have here? Firstly, 6 capacitors we have, and all capacitor voltages can be initialized independently. You'll find no contradiction. So there will definitely be 6 poles. And as usual, the dominant pole will be from CL. So let's write that alone. That's going to be CL, and you will make all the other capacitors to to go to 0. What is the dominant pole? Yeah, the output resistance. So looking up you have a PMOS cascode, looking down you have NMOS cascode, parallel combination of the two. So I'll just write it as some G0 by CL. You guys know it. And again all the other poles you will approx Pj, I'll just say the conductance at that node by capacitance at that node. That's all, right? No need to look into details. Sorry?
So that CL parallel to that will the same voltage will be there.
I didn't understand.
Voltage will be same CL and
No.
that's what we assume.
Okay, see, if that symmetry argument, I mean, see there the idea was it is kind of symmetric except this connection, right? But right now this, even if you don't have this connection, the circuit will not be symmetric, right? Because the capacitance can be different, right? I mean the CL is the output load you have, here this is the parasitic capacitor. So they need not be equal, I mean they won't be.
But even if we consider the resistance provided by the lower transistor, then again it will form the symmetry that the one you ignored.
Or not? No, that's what it will be symmetrical if we don't consider the load capacitor, right? The moment I put a big load capacitor here, this is not symmetrically loaded, right? So symmetry is not there. So you can't use any symmetry arguments when you are calculating poles and zeros.
What I am saying, you are considering R0 tending to infinity.
Of the NMOS alone, so that I can make this node to be 0.
Yeah. So even if we not consider that to infinity,
Okay.
then again it will form the symmetry.
No, it will still not be symmetric, right? Why will it be symmetric? First of all, there is no symmetry here. The moment you add capacitor, especially when I go and put a large load capacitor here, the capacitance here will be, let us say I call it some Cx, I mean, I don't know, C4 or something. C4 will not be equal to Cl. So that itself breaks symmetry. Because all the capacitors here are parasitic capacitors. But this one also includes the load capacitor that the OTA is driving. Okay. So even when you try to find the common mode transfer function, you can't use any symmetry arguments because this is load capacitor kind of makes it asymmetrical. Okay. For DC calculations you could do because we don't consider capacitors. So for common mode excitations we saw this kind of become symmetrical. That's only for DC. The moment you put a capacitor, that no longer will be the case. Especially, I mean, you can only at DC it will be symmetrical. At higher frequencies it need not be. That's the point. So this is okay. So then let's look at zeros. So how many zeros? Do you think we'll have 1 0 here? Can I short one capacitor at least in the network without the output going to 0? Which capacitor? Huh? Okay, we have left side, right side, top, middle, bottom. Top of, yeah, let's say I can short this guy, nothing happens. Okay. Can I short one more capacitor? This also I can short, nothing happens. Something else? I mean, see, loosely speaking, right, I am taking the output from this point. So in principle, to get a finite output, this much is enough for me. Even if nothing comes from this branch, it is okay. So even if I short all the capacitors in this branch, we'll still get non-zero output. Okay. So now this branch is not operational, left side branch, but still that is okay because we'll have small signal current from the right side bottom half. So 4 zeros totally. Okay. So we'll have 4 zeros. Again, let's not try to find the 0 location. It's not trivial here. But one thing is for sure, if you have a large load capacitor, and because of the fact that the output resistance or the output conductance is very small, this will be the low frequency pole, and all other poles and zeros will be typically be much far apart. Okay. And
But this MOSFET, the bottom one, left one,
yeah,
its current will flow through short circuit. Right?
correct. That's okay.
That MOSFET, the right side,
Mm-hmm.
its current will not flow through.
No, see, these are now two independent halves, right? you are correct. If I short this, this small signal current will flow here, nothing comes here. But that is okay because we'll still have a small signal current due to this guy. Right? The idea is I don't want the output to go to 0. That's all. I don't want the output you expected. At 0, the output will become exactly 0. If it is not 0, it is okay. Right? This is okay. So these are the 4 capacitors I can short. So 4 zeros. And again, dominant pole we'll find it. And other non-dominant poles we can approximate as conductance at that node by the capacitance at that node. And we'll assume that this is a low frequency pole and all the other things are happening at a frequency much further away. Okay. So once again, if I try to roughly sketch the Bode plot of the transfer function of this guy, we'll have a large DC gain. And then you have a very low frequency pole P1. And then all the other poles and zeros will occur far apart like this. So once again, for all practical purposes, we can approximate it like a first order system. Okay. Something like this. So we'll approximate this guy as some first order system like this. Okay. And this P1 is the dominant pole that is formed by the output conductance and the output capacitance. So, and for that matter, all the single stage OTAs that we have seen so far, you can typically approximate it like a first order system, assuming that the dominant pole is much lower frequency and all the other all the other poles are occurring further away. So typically that's how we model a single stage OTA. So we assume that we have a transconductor. So with some short circuit GM, and in a single stage OTA, this short circuit GM is the GM of the differential pair. And then we just have an output conductance G0 and an output capacitance here. So this is the first order system, and that's how we will be modeling our single stage OTAs like this. Right, so here again the pole is basically G0 by C. So all the OTAs that we have seen, namely the 5 transistor OTA, all the cascodes that we have seen, right, the telescopic cascode, folded cascode, gain boosted, we'll roughly model it like this to make life simpler.